Okay, I'll admit, going through that entire unit circle is a lot of work, and if you have to spend a lot of time memorizing this, you're really wasting your time. There's an easier way to deal with all of this, and the first thing that I would have to say is that as long as you remember what's happening in the first quadrant, you remember what's happening in every quadrant. And I'll show you why that is. First of all, you'll notice I have a square driven in here, and I remember that when I had a square before, what I did was I came up with a special right triangle. So I can imagine here, and I'm going to just really lightly dash this in yellow here for the moment, if I were to draw a nice right triangle right here corresponding to that slice right here within my right triangle, I would be containing the pi over 4 right triangle, and in that pi over 4 right triangle, I know that I get my coordinates of radical 2 over 2 and radical 2 over 2, right? And that's due to the ratios of the sides of this right triangle. Now let's do the same thing. How would we get it if we were talking about our uh, 30-degree right triangle, which is to say pi over 6. Well, if we're dealing with the angle pi over 6, remember that the ratio was that you had a right triangle of 1 half and radical 3 over 2, right? So let's see, if I were to deal with it, here I could draw a nice right triangle this way by pretending that I'm going over here to this point. And if I do that, sorry, let me come over here. Here's 1 half. Let me see if I can make this look a little bit better because I'm a little bit off in my aim right here. If I take my right triangle to this point right here along the right triangle, I have a side with a length of 1 half and a length of radical 3 over 2 along this adjacent side. That corresponds to my pi over 6 right triangle. So right here, as long as I remember, I've got radical 3 over 2 as my x-coordinate and 1 half as my y-coordinate. Then finding my sine, cosine, and tangent of, let's say, pi over 6 is really, really easy. Cosine of pi over 6 corresponds to the x-coordinate, and so that is radical 3 over 2. Sine of pi over 6 corresponds to my opposite side, which is 1 half, that's the y coordinate, and of course taking y over x, tangent of pi over 6 gives me a ratio of 1 half divided by radical 3 over 2, which is to say 1 over radical 3, which is to say, when I rationalize the denominator, radical 3 over 3. And that's what I'd want. Now, how about some of these other ones? Well, let's try it with, let's see, if we went to the pi over 3 right triangle, we'd be doing essentially the same thing. For the pi over 3 right triangle, however, we've got 1 half and radical 3 over 2, and those correspond to the the cosine of pi over 3 as the x-coordinate, and the sine of pi over 3 as the y-coordinate. Kind of interesting. All we're really doing is just matching x and y coordinates. And if that's the case, then if I'm asked to find what is the cosine of pi over 2, well, then I look for my x coordinate here at pi over 2, and whoop, there it is. That's 0. And if I look for my y coordinate, that's my sine of pi over 2. That's equal to 1. Now, if we wanted to get the tangent of pi over 2, we might find we had a little bit of a problem. The problem for us is that if we take the value of sine and divide it by the value of cosine, we get 1 over 0, which is undefined. And so we do not actually get a value for the sine of a right triangle like tangent pi over 2. Right? So we could say some similar things right here. For example, we might note that we could get a cosine of 0 if that's the case, and we know that's equal to 1, and we can get a sine of 0 and say that's equal to 0 because that's the y coordinate at that position. Any other coordinate that we look at is going to look like this triangle, this diagram, only reflected into the proper coordinate, coordinate 2 or 3 or 4, right? We're just looking at all of the different ways that we can put these positions in here and use those. And we're going to get to how we do that.